Indeterminate forms in L'Hopital's rule. Essential question, how do I use L'Hopital's rule? We want to use limits to analyze the behavior of functions. In this particular case, we're wanting to look at what happens close to 1. And when we find that we substitute 1 into the numerator, we get 0, and the denominator, we get 0. So it's what we call an indeterminate form, which means we may be able to find a limit or we may not. In the past, we've had problems like this. In the past, we've used a cancellation technique to be able to find a limit. We actually used some algebra, and we filled the hole by eliminating that common factor, and then we had a continuous function where we evaluated the continuous function and found that it was 1/2. We also took a look at a special limit that had sine of x over x, where we used the squeeze theorem to prove that it was equal to 1. In this case, we're not able to use our past techniques, and I have to introduce a new one, and that new one is called L'Hopital's rule. L'Hopital's rule has some requirements, though. The numerator and denominator functions have to be differentiable, and the derivative of the denominator cannot be equal to 0 except possibly at the value you're taking the limit of. When we have this 0 over 0 situation, or an infinity over infinity situation with some combination of plus or minus infinity, then you can take the limit of the quotient of these two functions is equal to the limit of the derivatives of these two functions as x approaches a. Why does that work? Well, graphically, let's talk about it. These two functions, their value at a is 0, so these are roots. Instead of using the functions, let's use their linearizations. Using their linearizations will give us great approximations for what we're doing. So here is the quotient of the two functions in their linearization form. That reduces to the slopes, and we know that slopes are derivatives. And so that's why we're seeing this happening, L'Hopital's rule is happening. Now the actual proof goes like this. We start with the limit of the quotient of the two derivatives, and we evaluate the two derivatives at a. Use the definition of derivative, which is the limit of the difference quotients for both functions. And here's the quotient of two limits, which is the same as the limit of the quotient. We can now simplify this quotient, and we know that these are roots, so that is a 0, this is a 0, and now we get the functions back. So the derivatives evaluated at a are equal to the limits of the functions as you get close to a. Now, how will this apply? First thing is you should always determine whether you can use L'Hopital's rule. So substitute 1 into here, we're going to get 0. Substitute 1 in here, we get 0. That's what this is for. Always make sure you can apply it. Once that's happened, then you take the derivative of the numerator and denominator, and you will get this form, which can simplify to 1 over x, and you can evaluate it, and it is 1. Let's take a look at another form. Again, as x approaches infinity, the numerator is getting closer to infinity, the denominator is getting closer to infinity. Again, L'Hopital's rule will apply. Take the derivative of the numerator and denominator, and you get this. Notice that we still have an indeterminate form. So we are allowed to do a second application of L'Hopital's rule. So we're right here, we're going to take the next derivative, and you can see that the numerator dominates the quotient, and we're going to get infinity. Let's take a look at another example, and again, this is an infinity over infinity situation. We're going to use L'Hopital's rule. Notice we have powers in the numerator and denominator. Instead of going to L'Hopital's rule again, think about simplifying. And since they're powers, let's take a look at that. And when we simplify it, we have this simple expression, and now the denominator dominates, and we're going to get a 0. Be careful when you're taking a look at quotients, because in this case, L'Hopital's rule does not apply. In the numerator, it will be 0, but in the denominator, as you get close to pi, you're going to get close to -1, and this value will actually be 2. So the answer is 0. And students who blindly go about just using L'Hopital's rule without checking will get this as the answer, and that is not correct. Let's take a look at a different kind of indeterminate form, and that's 0 times infinity. And 0 times infinity, we can deal with it by making the product into a quotient. And you can do that very easily by doing one of these two things. Let's go ahead and do that. Before we do that, let's make sure this is an indeterminate form. This is 0. And remember, the natural log of x looks like this. So as you get close to 0 from the right-hand side, this is going to be negative infinity. So this is an indeterminate form. Rewrite as a quotient. And so I'm going to write natural log of x all over 1 over x. And now this is going to be negative infinity over negative infinity. All right, on the next slide, I actually take the derivatives of the numerator and denominator, do some simplifying, and then evaluate. The other indeterminate form is a difference of the infinities, infinity minus infinity. And again, the idea is to convert to a quotient. All right, and in this case, let's go ahead and show you how to do that. I'm going to take the limit. Oh, by the way, I guess I should evaluate. This is infinity minus infinity. And now I'm going to take x approaches pi halves from the left-hand side. I'm going to write 1 over cosine x minus sine of x over cosine x and try to get this into one quotient. I do that in the next slide where I get it into one quotient, and I can see that indeterminate form is 0 over 0 now. Take the derivative of numerator and denominator and then evaluate. The last type of indeterminate form is with powers, and when you have 0 to the 0 power, infinity to the 0 power, and 1 to the infinity power. Now to deal with this kind of limit, what we're going to do is we're going to take the natural logarithm. Why do we do that? Well, when you take the natural log of both sides, then you're going to be able to use one of the properties of natural log where you take the exponent and it becomes a factor, and now you're dealing with a product instead of a power. Okay, let's take a look at a problem in which I do that. What I'm going to do is I'm going to change that to the limit as x approaches 0 from the right-hand side, and I'm going to do e to the natural log of x to the x power. Now remember, these undo each other, and what's nice about this is now I can take this exponent and write it as a factor. Okay, so what I've done is I've taken this and I've written it as a factor. Now what I want to do is I want to figure out what this value is, and whatever that value is, that limit is, then I'll be able to continue. So I'm going to take the limit as x approaches 0 from the right-hand side of x, natural log of x. And I hope you remember we just did this a few minutes ago. We did it by making it a quotient, and so we went natural log of x over 1 over x. And we ended up getting 0 as our answer. If you want to look back a couple of slides, you can go ahead and do that. So this value right here goes to 0. So this is going to be equal to e, and now we know that this limit goes to 0. And so the answer to our question will be equal to 1. Okay, here are some problems from your homework. You are to do the odd problems, and here are the evens. If you take a few minutes to go ahead and do some of these problems and check your answers, the next slide has the answers. And here are the answers. Again, this is from your homework, and if you want to try a couple of these are the even problems. Your odds will be what you do for your exercises. And here are the answers. And you can see 44, L'Hopital's rule doesn't even apply.